Everyone has heard of black holes. They are the most extreme objects in the universe, regions where gravity becomes so powerful that not even light can escape. But what if the universe has an opposite? A place you can never enter, a place that only pushes matter, energy, and even light outward. A white hole. The question is simple. If physics allows it, why has no one ever seen one? In the simplest terms, a white hole is the theoretical opposite of a black hole. A black hole pulls everything inward. A white hole would do the reverse. It pushes everything outward. Nothing can escape a black hole. Nothing can enter a white hole. This idea comes directly from Einstein's theory of general relativity. And here is the key point. White holes are not an invention. They appear when physicists solve Einstein's equations completely. The story begins in 1916, when Carl Schwarzschild found the first exact solution to Einstein's equations. At first, this solution described black holes, but later, physicists realized something strange. The full mathematical extension of this solution also contains a region that behaves like a white hole. In the 1960s, physicists like Igor Novikov explored this idea further. They showed that if you extend space-time fully, you don't just get black holes, you also get white holes and even bridges between regions of space-time. This was the first time scientists seriously considered that white holes might be more than just math. However, something didn't add up. Black holes had a clear formation process. Massive stars collapse under gravity. But white holes? There was no known physical process that could create them. No collapsing star, no explosion, no known mechanism. And this is still true today. White holes are allowed by equations, but not supported by known physics. Physicists began testing whether white holes could actually exist, and one of the first problems they found was stability. If a white hole existed, even the smallest disturbance, like a single particle falling toward it, could destroy it. In other words, white holes are extremely unstable. This means even if they formed, they likely wouldn't survive long enough for us to observe them. Then came an even deeper problem: entropy. In physics, entropy measures disorder, and in our universe, entropy always increases. Think of a broken glass. It doesn't reassemble itself. But a white hole behaves like the opposite. It looks like matter suddenly organizing and coming out of nowhere. This goes against the natural direction of time. Because of this, many physicists believe white holes are not physically realistic, at least not in classical physics. Now let's compare theory with observation. Black holes were once theoretical too, but in 2015, scientists detected gravitational waves from two black holes merging. And in 2019, the Event Horizon Telescope captured the first image of a black hole. These were historic moments. But for white holes, there has never been a confirmed observation. This is the biggest difference. Black holes are proven, white holes are not. At one point, scientists thought they might have found white holes. In the 1960s, quasars were discovered, extremely bright objects in distant galaxies. Some physicists suggested maybe these are white holes ejecting matter. But later research showed something else. Quasars are powered by supermassive black holes, not white holes. So one of the best candidates for white holes was ruled out. For a while, white holes faded from serious research, but then they came back through quantum physics. This time, not as giant cosmic objects, but as something much smaller and more subtle. In 2018, physicist Carlo Rovelli and his team proposed a radical idea. They suggested that black holes might not end as singularities. Instead, after a very long time, they could transition into white holes. This process is sometimes described as a quantum bounce. The idea is simple but powerful. What goes in eventually comes out, but not instantly.
It could take billions or even trillions of years. Why is this idea important? Because of one of the biggest problems in physics, the information paradox. If something falls into a black hole, is its information lost forever? According to quantum theory, information cannot be destroyed. White holes provide a possible solution. The information is not lost, it is released later. Many people imagine this scenario. You fall into a black hole and exit through a white hole somewhere else. This idea is linked to wormholes, tunnels through space-time. Mathematically, such structures can exist, but in reality, they are unstable. They collapse too quickly. So for now, this idea remains in the realm of theory and science fiction. Now we reach the biggest idea of all, the Big Bang, the beginning of the universe. Everything expanded outward from a single point. This looks very similar to a white hole. Some physicists have explored this connection, but we must be careful. This is not proof, it is only an analogy. Still, it shows how white holes connect to the origin of the universe itself. White holes may or may not exist, but their importance goes beyond that. They force us to ask deeper questions. Does time only move forward? What happens inside black holes? Is information truly lost? How did the universe begin? White holes are not answers. They are a doorway to bigger questions. Maybe black holes are not the end. Maybe they are part of a cycle, and white holes are the other side we still don't fully understand. Right now, they exist between theory and reality, between science and mystery.